Welcome back, quadrature fans. My name is Professor Theoremus Antiquitas, also known as Marian Alana, and come and meet the family behind the scenes. So let's go. This is the family. Welcome. Yeah, that's my wife Susan, Anastasia, and Paul. All right. So today we're going to do lessons learned and how I tackled quadratures. So we're good. All right. So, this thing's getting hot. Lessons learned. Oh well. Basically, I always wanted to understand calculus, and unfortunately, when I learned it, I didn't really understand it. So that kind of bugged me a little bit. And so I kept dabbling, and here's the kind of doodles that I drew. So here's our basic setup for y equals x squared. Basically, this is what I knew. I knew that this wedge here was 1/8 of this big wedge over here. And that was just by rubber band geometry. So what that meant is, well, that would mean this would be in a proportion of 1, and then this whole thing would be in a proportion to 7, 1 to 7, or 1/8 and 7/8 of this whole big wedge. So I kept thinking, okay, is there a way to tackle this using just algebra? Can I get this algebraically? And I didn't know what to do with this wedge, how to proceed with this funny looking wedge right here. So that was a puzzle, and don't know, I couldn't do it. So for years I was stuck here, not knowing what to do. And I was kind of resistant of going the route of the tangent, you know, tangent first and then area. I didn't like that approach, but I was forced to kind of concede that, you know, looks like I can make some progress if I do the tangent right here, because then I can say, well, this funny looking wedge here, well, what is that? Well, that consists of 3 shapes. A constant, a linear term, linear, and a quadratic. And the tangent gave me the proportions of 1 to 2 to 1. 1, 2, 1. Well, those are the magic proportions that I needed. And then I could, maybe then I could proceed algebraically. And so this looked good. So basically, the setup was, okay, K2 times this big wedge. Let's say we go from 0 to a to 2a, 0a squared 4a squared, right, times height times base, 4a squared times base, 2a. That equals the area of these, right? And so, okay, the area of this, that would be some ratio k2 times a squared times a plus this one, 0 to a, which would be basically a squared, 2a squared, a squared. Right? So plus a squared times a, and that's 1, plus 1/2 because it's a triangle. 1/2 times 2a squared times a plus, and this third one is the same as this one, 1 times a squared times a. And you've seen this before. K2 times 8a third equals K2 times a to the third plus a to the third plus a to the third plus, am I doing something wrong? Oh, not 1. K2 times a to the third. And the a to the third basically falls out. And you get K2 times 8 equals K2 plus 1 plus 1 plus K2. So 6K2 equals 2, from which we get K2 equals 1/3. Pretty cool, huh? But what bothered me was that, in order to get this, I had to know what the tangent is, right? Because that, once you know the tangent, well, that gives you your height over here. And I didn't like that. I didn't understand it really. And then I watched a video by Professor Wildberger called Famous Math Problem 10a and b, and I didn't understand it at first, and he said it was high school stuff, but that just shows you. But he did mention these 5 properties called, well, let's name them. There's additivity, these are properties of areas. Linearity, translation, which is a big one. That's the one that I needed. Dilation, and this one matched closely to my rubber band geometry, so I picked up on that. And then normalization. Well, I knew that, K2 equals the area of this wedge divided by area of the box, right? The area of this wedge divided by area of this box, well, that's already a normalized K factor. This is normalization. So I got this. I basically understood all of these, but I didn't have this one. This was the key. This turned out, and what is that? Translation. Well, this is on the x-axis. Basically, superimpose the t-axis right on top of the x-axis, but say t equals 0 minus a plus a. You see how the relationship is between the x and the t? basically we're saying x equals a plus t. That's translation. And once you have this, well, you don't need the slope anymore, because look, you plug in y equals x squared, so y equals a plus t squared. And that equals a squared plus 2at plus t squared. But look, let's say this is on the t-axis. T equals 0 and t equals a. So if you plug in t equals a, well, here you get 1, that's always. How about here on the linear? You plug in 2a times a, you get 2a squared. That's it. And how about the quadratic term? You plug in t equals a, you get a squared. You plug in t equals 0, you get 0. So it was making sense, and I didn't have to work it from the tangent perspective. I didn't need the tangent, even though, whoa, here it is, here's the tangent, boom. So simple. T equals 0. The only one that gives rise to slope is linear term. Everything else is 0, but I didn't need it to start out with, because translation gave it to me. So that's kind of nice. So that's kind of how I arrived at this. So with the help of Professor Wahlberger, I approached it with kind of my own way. It's not exactly identical to what Professor Wahlberger does, but underneath the hood, his stuff and my stuff are basically the same thing. Just a different twist to it. But the cool thing I found is that, this is for slope. Well, I could do stuff for the area too. I'm not for area, for the slope. So I did the area, but I could use the same setup to find the slope, and basically it's right here. You're looking at it. There's the slope, the tangent slope at t equals 0, which is x equals a, and we just got it like that, without having to go to limits or anything like that. It just popped right out. Very simple. So that's kind of how I pursued this thing. It took a number of years to figure it out, but I just kept doodling and laid it aside, came back to it. And so that's what it is. So there we have it. Alright, so remember, before there was calculus,
There was
quadrature.
quadrature.
You got it.